So just to show you how powerful this approach is of treating multiple objects as if they were a single mass, let's look at this one. This would be a hard one. We've got a 9-kilogram mass hanging from a rope, and that rope passes over a pulley, then it's connected to a 4-kilogram mass sitting on an incline, and this incline is at 30 degrees, and let's step it up. Let's make it hard. Let's say the coefficient of kinetic friction between the incline and the 4-kilogram mass is 0.2, and that's the coefficient. So there's going to be friction as well. Again, if you tried to solve this the hard way, it'd be challenging. It's doable, but you're going to have multiple equations with multiple unknowns if you try to analyze each box separately using Newton's second law. But because these boxes have to accelerate at the same rate, well, at least at the same magnitude of acceleration, then we're just going to be able to find the system's acceleration, or at least the magnitude of it, the size of it, right? This 4-kilogram mass is going to have acceleration this way of a certain magnitude, and this 9-kilogram mass is going to have acceleration this way, and because our rope's not going to break or stretch, these accelerations are going to have to be the same. So we get to use this trick where we treat these multiple objects as if they were a single mass, and the acceleration of a single mass only depends on the external forces on that mass. So we're going to only look at the external forces, and we're going to divide by the total mass. So what would that be? If we wanted to find the acceleration of this 4-kilogram mass, let's say, what's the magnitude of the acceleration? Well, look at this 9-kilogram mass is much more massive than the 4-kilogram mass. And so this whole system is going to accelerate in that direction. So let's just call that direction positive. So that's one weird part about treating multiple objects as if they're a single mass, is defining the direction which is positive is a little bit sketchy to some people. They might find this sketchy. We're just saying the direction of motion this way is what we're calling positive. And that works just fine. So when I plug in up here, when I go to solve for what is the acceleration, I'm going to plug in forces which go this way as positive and forces which go the other way as negative. So let's do this. What do I plug in up top? What forces make this go? Well, the force of gravity on this 9-kilogram mass is driving this system. This is the force which makes the whole system move. If I were to just let go of these masses, they'd start accelerating this way because of this force of gravity right here. So that's going to be 9 kilograms times 9.8 meters per second squared. And that's going to be a positive because it's making this system go. There's no other forces that make this system go. So now I'm only going to subtract forces that resist the acceleration. What forces resist the acceleration? Well, the gravity of this 4-kilogram mass resists acceleration, but not all of the gravity. The gravity of this 4-kilogram mass points straight down, but it's only this component this way which resists the motion of the system in this direction. And what is this component? This is mg sine theta. So if that doesn't make any sense, go back, look at the videos on inclines or the article on inclines, and you'll see that the component of gravity that points down an incline parallel to the surface is equal to mg sine theta. So I'm going to have to subtract 4 kilograms. 4 kilograms times 9.8, because that's g, meters per second squared, times sine of the angle, and my angle's 30. So I'm going to do sine 30 degrees. Okay, we need some more room up here because there's going to be more forces that try to prevent the system from moving. There's one more force. The force of friction is going to try to prevent this system from moving, and that force of friction is going to also point in this direction. It's not equal to mg sine theta. It's equal to, right, remember the force of kinetic friction, going to be equal to mu k times Fn, and the mu k is going to be this 0.2. You got to be careful though. The Fn is not just equal to mg. And the reason is that on an incline, remember the normal force points this way. So the normal force doesn't have to counteract all of gravity on an incline. It just has to counteract that component of gravity that's directed perpendicular to the incline. And that happens to be mg cosine theta for an object on an incline. And again, if that makes no sense, go back, look at the video on inclines, or look at the article on inclines, and you'll see that this component of gravity pointing in to the surface is mg cosine. That means the normal force is mg cosine because there's no acceleration in this perpendicular direction. and I have to multiply by 0.2 because I'm not really plugging in the normal force up here or the force of gravity in this perpendicular direction. I'm plugging in the kinetic frictional force. This 0.2 turns this perpendicular force into this parallel force this way. So I'm plugging in the force of kinetic friction. It just so happens that it depends on the normal force. That's why I'm plugging that in. So I'm going to need a negative 0.2 times 4 kilograms times 9.8 meters per second squared. So that's a 0.8. And then I need to multiply by cosine of the angle. And in this case, the angle is 30 degrees. All right. And now, finally, I divide by my total mass because I have no other forces trying to propel the system or to make it stop. And my total mass is going to be 13 kilograms. You might object. You might be like, wait a minute. There's other forces here. There's this tension going this way. Why don't we include that? Well, that's an internal force. And the whole benefit, the appeal of treating this two-mass system as if it were a single mass is that we don't have to worry about these internal forces. Yeah, that force is there, that tension, but you can also have that tension over here. And on this side, it's resisting the motion because it's pointing opposite the direction of motion. And on this side, it's helping the motion. It's an internal force. The internal forces cancel. That's why we don't care about them. That's what this trick allows us to do. By treating this two-mass system as a single object, we get to neglect any internal forces because internal forces always cancel on that object. And so if we just solve this now, we just solve this, calculate, we're going to get 4.75 meters per second squared is the acceleration of this system. So this 4 kilogram mass will accelerate up the incline parallel to it with an acceleration of 4.75 meters per second squared, and this 9 kilogram mass will accelerate downward with a magnitude of 4.75 meters per second squared. Remember, if you're going to then go try to find out what one of these internal forces are, I mean, they're there. We neglected them because we treated this as a single mass. But you could ask the question, what is the size of this tension? Oftentimes that's like a part 2 because we might want to know what the tension is in this problem. Well, if we do that, now we can look at the 9 kilogram mass individually. So I can say, all right, just the 9 kilogram mass alone, what is the tension on it and what are the forces? I can find the forces on it simply by saying that the acceleration of the 9 kilogram mass is the net force on the 9 kilogram mass divided by the mass of the 9 kilogram mass. Now, this is just for the 9 kilogram mass. Now, I'm done treating it as a system. This trick of treating this two-mass system as a single object is just a way to quickly get the magnitude of the acceleration. Now that I have that, and I want to find an internal force, I'm looking at just this 9 kilogram box now, and I can say that my acceleration is not 4.75, but negative 4.75, at least if we want to treat downward as negative and upward as positive, which is often done, then I have to plug this magnitude of acceleration in as a negative acceleration because the 9 kilogram mass is accelerating downward. And that's going to equal, all right, what forces are there on the 9 kilogram mass? I called downward negative, so that tension upward's got to be positive, but then minus the gravity, force of gravity on the 9 kilogram mass is 9 kilograms times 9.8 meters per second squared, and then I divide by 9 kilograms. I don't divide by the whole mass. I'm done treating this system as if it were a single mass. I'm now looking at an individual mass only, and we go back to our old normal rules for Newton's second law where up is positive, down is negative, and I only look at forces on this 9 kilogram mass. I don't worry about any of these now because those aren't directly exerted on the 9 kilogram mass, and at this point, I'm only looking at the 9 kilogram mass. So if I solve this, now I can solve for the tension. And if I solve for the tension, I'm going to get 45.5 newtons, which is less than 9 times 9.8. It's got to be less because this object is accelerating down, so we know the net force has to point down. That means this tension has to be less than the force of gravity on the 9 kilogram box. So recapping, treating a system of masses as if there were a single object is a great way to quickly get the acceleration of the masses in that system. Once you find that acceleration, you can then find any internal force that you want by using Newton's second law for an individual box. You're done treating as a system, and you just look at the individual box alone like we did here, and that allows you to find an internal force like the force of tension.